Hi, my name is Saigopal Nelaturi. I'm the second representative from the University of Wisconsin in these talks. I'm going to be talking about configuration modeling, or what the connections are between shapes, motions, and signal processing. And this is research that we've been carrying out at the University of Wisconsin over the last couple of years. And let me get right to it. So the first thing I want to show you is a picture of a typical tooling setup in an automobile shop floor where you have a sheet metal part, a couple of fixtures, and a spot welding robot in yellow. The robot is moving around the static tooling, and our problem is to find configurations of the robot which does not cause collision or interference with the part and the fixture. Now, this is a ubiquitous problem in manufacturing planning and occurs in several applications such as robot motion planning, accessibility analysis, collision detection, interactive layout and fixturing, and so on and so forth. But at the same time, there aren't any effective solutions with existing software for industrial scale parts, simply because there are no solutions that work either interactively or in real time or fast enough. So what I'm going to do now is to show you a demo of software I've been putting together at my workstation in my lab. That shows interactive accessibility analysis. So in the center, you have a picture, you have a CAD model of the tooling layout, and on either side, we have voxelized models of the geometries interacting. And what I'm doing now is I'm going and clicking on different points on the work part surface from the voxelized model, and you can see interactively, I have a map of all the colliding orientations of the robot that are generated at each point. Okay, and so now this, you can see that it's generated on the fly right away as I go through different points on the work part. And so the focus of my talk today is to basically say why this problem hasn't solved before and what does it take to solve such problems, right? And the first concept we have to deal with is the unification of shapes and motions using a concept called the configuration space, which is basically the space of all relative configurations between the robot and the static tooling. So conceptually, though, you can look at a configuration space problem here, where we're transforming the problem of planning the path of a robot moving with a fixed orientation in the presence of these triangular obstacles to the configuration space where we are now planning the motion of a point moving around some other shapes, which are basically created by growing or offsetting the physical obstacles in a precise mathematical way by the shapes of the robot. And so once you have this construction, the configuration space is partitioned into three disjoint regions corresponding to the safe, contact, and prohibited regions. The safe regions are everything in white. The contact regions are the boundaries of the gray shapes, and everything inside the gray shapes correspond to obstacle spaces or the prohibited regions, where there's going to be interference. Okay? And for realistic parts, the configuration space obstacle looks quite complicated and is still a challenge to compute these things. And furthermore, when you add rotations to the degrees of freedom of the robot, you have 6 degrees of freedom for the rigid body moving in 3D space, and so the configuration space becomes 6-dimensional. And so how do you actually solve these problems? So the way we approach it is we compute these fixed orientation configuration spaces for each orientation of the robot. And we call each of these fixed orientation spaces a 3D slice. And we iteratively do this over an array of robot orientations and assemble it together and compute the entire 6D configuration space. So now the central question becomes, how do you compute these 3D slices? And this is where we come to the key idea, the key computation of everything that's going on in here. So the title of the slide is Geometric Computations with Signal Processing. So what we do is we first represent the robots and the physical obstacles, the tooling fixtures, and so on, as binary voxelizations, as I showed you in the video, just to refresh your memory. Here it is. And by computing the binary voxelization, you convert the shapes into functions. And once you've done that, we can use the Fourier transform in order to convert these functions from spatial domain to frequency domain. Okay? And now you can loosely think of these shapes as waveforms, if you like, in the frequency domain. And using this representation of shapes now, we can apply signal processing algorithms like convolutions and fast Fourier transforms, which can be used to very quickly compute each of those 3D slices on the GPU. And it's, the Fourier transform is one of the flagship parallel applications that is on the GPU, and CUDA has free implementations as well. And each slice takes milliseconds for convolutions that fit on the card. And it depends on, and the whole problem, time complexity depends on the spatial resolution, not the geometric shapes. And once we compute each of these slices in a matter of milliseconds, we stack all the slices and we're done. And each of, and then you can see that we can query the configuration space very quickly to create those maps, okay, at each point. And the applications of this technique do not just stop at accessibility analysis or path planning, but extend to things like interactive planning, as I just showed you, reverse engineering, workspace computation, sweeps, and collision detections, and so on. And I would be happy to talk about any of these applications with you offline if you're interested. And finally, a shout out to all my colleagues at the Spatial Automation Lab. And I'd like you to draw your attention to that, the caption under the last picture there. Thank you.